Bismillahirrahmanirrahim. In today's video session, we will discuss cyclic redundancy check, that is called CRC. CRC is basically an error detection method. It is based on the binary division. It is quite simple to implement in hardware and can be easily analyzed mathematically. CRC generator is basically an algebraic polynomial represented as a bit pattern. So bit pattern is obtained from the CRC generator using the following rule. For example, if you are generating CRC for CRC generator, if it's given in the form of polynomial, so how can you obtain bit sequence? So here 1 is 1, 6 0 x1, so you can write 1. X2 is missing, so you need to write 0 for x2. X4 x3 is here, x4 is available, x5 is missing, so you can write 0 for x5, x6 1, and x7 1. So you can write coefficient. If any coefficient is missing or any x is missing, so you can simply write 0 on that particular place. What are the steps involved? The steps at the sender side, we can write here the steps involved for calculating CRC. Steps involved. First, at sender side. So how can we calculate CRC at sender side? First, bit streams are given, sometimes in the form of polynomial. So bit string are information that need to be transmitted, or we can say message m of x. It uses modulo 2 arithmetic. Modulo 2 arithmetic is basically exclusive OR operation. In the third step, polynomial generator. Polynomial generator is basically a generator. It is called g of x. Both the parties, sender and receiver, must agree upon the polynomial generator. It is basically a bit sequencer, sometimes given in a polynomial, that both the parties should know about polynomial generator. On the basis of polynomial generator, we can generate CRC and we can detect error at the receiver side. Fourth one is the sender generated basically bit sequence called FCS. This is called frame check sequence. And how it can calculate FCS? M of x divided by g of x. M of x plus the number of the order of polynomial generator, and you should add that number of zeros here, and then you divide on polynomial generator. If let's suppose a polynomial generator is order 3, so you need to add 3 zeros here, and then you can divide on the polynomial generator, so you can get FCS. FCS is nothing but a remainder. So in the fifth, you can calculate the transmitted bit pattern, that is the message signal plus the remainder. Remainder is basically sometimes CR, you can say FCS, and then you transmit this bit pattern to the receiver side, transmit on the channel, and then at the receiver side, steps involved at the receiver side. So after receiving T of X is basically the message signal plus CRC, and divide it again by G of X. G of X is the bit pattern for which both the sender and receiver are agreed upon before transmission. So first let divide T of X on G of X. Second step, if there is remainder, F remainder means error, there is error. If no remainder, so no error, so otherwise no error. So we have two cases. If we get remainder, so the data might be distorted during the transmission or garbled during the transmission. If there is no remainder, it means we received the same bit pattern that is transmitted by the transmitter. So let's solve an example so that we could properly understand CRC. So let's take an example. If message or data is given, example, M of X or data is given in the 10010, and polynomial generator is also given for which both the parties must agreed upon before transmission. So how can we calculate T of X? Or we can simply say how CRC will be calculated at the sender side. So first we know the order of G of X is 0, 1, 2, 3. So we can say R is 3. So the first step 1, M of X, which is 1, 0, 0, 1, 0, 0, and as G of X is 3, so add 3 zeros here, 3 zeros, 1, 2, 3, and then divide M of X or G of X. So we know M of X is 1, 0, 0, 1, 0, 0, and 3 bits are basically added, so you can write 3 bits and then you can divide this on G of X, and G of X is basically 1, 1, 0, 1, so you can use 1. After using a 1, 1, 0, 1, use modulo 2. Modulo 2 is basically exclusive R. Exclusive R A is equal to 0, same number of bits, and A exclusive R B is equal to 1 for different bit. So we have same number, so we will get 0 here, 0 here, 1 and 0. Discard the starting 0 and you can bring this 0 here. Again 1, 1, 1, 0, 1, exclusive R, so 1, 0, 1, 0, discard 0 and you can bring this 0 here. Again 1, so 1, 1, 0, 1, so you have 1, 1, 1, 0, discard 0, You can bring this 0 here, like this 0 that we added, and then again you can use 1, so 1 1 0 1, we can get 1 1 0 0, we got 2 0, so you can bring this 0 here. Okay, so discard this 0, so we have 2 0, so again discard the other 0 and bring this 0 here, the other 0, and again 1, so 1 1 0 1, so 1 0 0 0, so you need to discard this 0, the remainder, and t of x would be equal to, this is basically CRC, so m of x plus CRC, that is m of x is basically 1 0 0 1 0 0, we know, and you can add this remainder 0 0 1, which is equal to t of x. So you can calculate the transmitted bit pattern at the sender side using CRC. However, at receiver side, so how the receiver will analyze that there is no error or there is some error, so the receiver will receive t of x in the form of 1 0 0 1 0 0, and the receiver will again, so this is receiver side, steps involved at the receiver side for error detection, so 1 0 1 0 0 and 0 0 1, again the receiver will divide the same bit pattern on the g of x, and g of x is given 1 1 0 1, so use 1, you will get 1 1 0 1, so 0 0 1 0, discard this now, you can bring 0 here, again you can use 1, so 1 1 0 1 1 0 1 0, discard this 0, and then you can bring 0 here, you can use 1, so 1 1 0 1, and then 1 1 1 0, discard this 0, and you can bring this 0 here, again 1 1 1 0 1, so 1 1 0 0, discard 1 0, and you can bring 0 here, yeah, again you can discard the other 0, and then you can bring 1 here, and then you can divide 1, so 1 1 0 1, so 0 0 0 0, no remainder, so there is no error. Okay, if you change any bit here, so you will get some remainder, so in this way you can generate, and you can generate CRC, and at the receiver side you can detect particular error. Thank you.